So Ari is going to speak about part of the OpenAV project and more specifically a library that you are developed recently to connect hardware and software.
Check. Hello, everybody. As Stephanie introduced me, I'm Harry van Haaren. I'm the lead developer of the OpenAV project. And today I'd like to talk about the controller library that I've been working on. So as part of the controller library, I have a few demos and a couple of slides. The demos will take form of, there are two devices here in front of me, and I'll kind of hold them up and we can kind of show you what I've been working on. And yeah, hopefully we can kind of get you guys all a bit enthusiastic about using this kind of like what I call modern controllers together with Linux and Linux audio in general. And we can talk about how we can, as a community, support these devices, make it easier to program with them, for them, and enable users to use these in live performances on stage. So that's the ultimate goal that I think we're trying to get to. I'll jump straight in and basically give you a really brief overview of, okay, what are we talking about? What we're talking about is modern controllers. More on that later. Why should this be a library? So I've had various discussions with people, and there seems to be a few angles that we could take to support these devices. And I'm of the opinion that a library is a good idea. So what I've done is basically built this library, and now I'm going to throw it up. It's actually on GitHub. I published it yesterday evening. So for anyone who's code curious, do browse to github.com/OpenAV Productions/OpenAV Ctrla, I think. After the library, we'll talk about users and mapping. So what's the use cases and what do I mean by mappings? By mappings, we're talking about like the device has a slider. How do we move a software slider using that device, that kind of thing. I am going to try and get as many demos in. So there's a lot of stuff we can show here and kind of demonstrate from the simple usage of the controller library to much more complicated layered mappings with screens and all these kind of fancy things. And if there's time, I have bonus stuff here. So again, I'll probably open the floor to questions and see what people are interested in particular. And then we can take it from there and kind of make it a bit more interactive, hopefully. So I'll jump straight in. Let's talk about modern controllers. I found a couple of shiny images online. That's these. We have one of these guys right there, so I'll kind of demonstrate what they are. What do I mean by a modern controller or a next generation controller? I'm sure most of the people in the audience are familiar with MIDI controllers, so it's been around for quite a while. You plug in either an analog MIDI cable, or digital technically about details, or a USB cable, and that results in you can pull some bytes from a wire, and that you can interpret based on the MIDI protocol, and then you have a message that happened. That scales up to a specific degree, but in my opinion, once we get to these kind of devices, it's not capable enough anymore. And various manufacturers are now building these devices as USB HID devices instead of USB MIDI devices. That basically means it's a different protocol, it's more performant, it's more capable. I won't bog down the details of USB HID because I think it's covered on the internet in various places. What I will talk about is why I think that this kind of ties in with what we're trying to achieve. When we want to communicate with these devices, we need that USB HID support, and adding that to every application out there, every DAW, every sequencer, is a lot of effort. That's kind of tying into the library usage. So for now, basically, keep in mind, this is what I'm considering for most of the controller talk. Although I do intend to support old school, I'll say, MIDI controllers that just have faders and dials. This is more the focus, the more future forward-looking controllers that have multiple layers of complexity and a lot of capabilities. So when we talk about controllers, this is an APC 40. It was released in 2014. I jumped on it. I love this grid kind of interface for doing like live clip launching and these kind of things. It was released in 2014. It's a USB MIDI device, so this is the older variety, not like the devices that I have here. And when I started programming with it, I found an issue is that what we can't do is update this entire grid in one go. So if we stream all the MIDI bytes one by one to actually update each LED color, then it takes time. If you program them in a specific way, you can see it like swoosh across the device because of the time taken to actually send all those messages over the cable to update the state. So what I'm trying to say is there's a limitation of what USB MIDI can actually handle. And we're pretty much at that with these types of devices. So we need to look forward into other technologies, and USB MIDI or USB HID solves that problem. So another question might be HD screens. I'm sure somebody's thinking, hey, we can use like system exclusive MIDI messages to update. No thanks. Let's talk about APIs. If we need to use this USB HID type devices, then we need to have an API for that. If we all implement it, there's a lot of duplication of efforts. If we design an API and try and build a library under that, maybe we can save ourselves and each other a whole bunch of work. So what I'm looking at is essentially communicating between software and hardware. We want it to be easier from the software point of view, and we want it to be faster so that we can support things like HD screens on controllers, do updates of the entire device multiple times a second to provide a good user experience. And those are things that I consider requirements for tight integration. And I'll talk more about what exactly do I mean with tight integration in a few seconds. So those are some of the requirements that I was taking when we were designing or looking into this Ctrla library. So why do we actually need a library? I'll leave this image up for a second because I think it represents for quite a few users and musicians the current state of device support and Linux audio. We have a situation that MIDI devices are supported by most things. In particular, almost every DAW that I know of supports MIDI mapping. But does it support your Wiimote or your Bluetooth? I know certain DAWs do, I know others might not. Maybe we could convert the Bluetooth into MIDI using some script and then, but as an end result of those kind of hacks and fixes, the user experience deteriorates quite a lot. So what I'm hoping to achieve is to enable all of the devices on all of these various pieces of software. And to do that, I'm proposing this Ctrla library. So when I propose this library, what I'd like to kind of hand over to you guys in the audience and everyone watching the live stream is, as a developer in the audience, consider taking this library. If we implement support for it, what we get is the list of devices that are currently supported will be integrated with your application essentially seamlessly. Any devices that are after that point added to the Ctrla library are free to you as a developer, or if the musician or user has one of those devices, it will just work and there's no extra code to be written. So there's an abstraction in this library that allows us to plug in new devices under the API, and it essentially just gives all of the software those for free. So that's kind of a don't re-implement device support idea, particularly testing. So implementing the support for the device is quite easy, or relatively easy, I'll say. Testing it afterwards to make sure that everything does exactly what it should do is a real-time sync. So I'll show you these devices in a while. There's a whole bunch of buttons, and testing each one to make sure that the string label of what your API gives you back for that button, if they match, that kind of stuff it's boring and it's a time sink. So we should try and not do that over and over again, but rather do that once as a community and then benefit from each other's work. So how do we want to enable this? What I'm proposing is that we abstract away specific devices and instead think about events. If I press this button here, what actually happens is an event gets sent. In the MIDI terms, you get a note on usually, but in USB HID, it could be anything. You don't quite know. It depends on each device. So I'm suggesting that we abstract away the device specifics and that we use a C struct to represent an event, and that will be pushed to the application. So the application only looks at generic events. It does not understand a specific device. So it can get access to metadata about the device, but it doesn't understand fundamentally the USB HID that this device speaks. It understands the abstraction above it, which is this generic event layer. So an example I just used was the button, but we would have similar events for a slider, for an encoder, for what I call a grid. So that's like a 4x4 or an 8x8 matrix of buttons. So there's a lot of options there in terms of how we want to actually send those events up to the application. Similarly, there are functions for LED feedback, so that if we want to light up a particular LED on a device, there's an API to do that. So from an applications point of view, you have events coming in when something happens, and you have functions you can call to update the state of the controller. It's pretty simple in my opinion, but I'd love to hear feedback from you guys later, today, tomorrow, on email, whatever. So there's also an API to blit pixels to a screen. That's kind of the most prototypey part of the API right now because I'm kind of working through the details. I won't jump into the screen stuff, but if you do have interests in displaying things on controller screens, come talk to me after the talk or during the LAC, and I'd be more than happy to discuss it. So another angle is Linux support. Neither of these devices is natively nor supported by Linux kernel right now. It is, of course, theoretically possible to write a kernel module for them. They'll show up as an ALSA MIDI device, and we have to transfer these USB MIDI messages into ALSA MIDI events. And then we're back to step one, which is we don't actually have enough MIDI bandwidth to update this entire device, and there's no way we can update the screen either. So I don't see that as a good solution. So that's kind of the underlying reason for having developed Ctrla as well, is there's community-supported devices. So there are devices like these that we can understand the protocol that the device speaks, but it just doesn't happen to be upstream in the kernel. So from a user's point of view, if you plug it in, nothing happens, aka broken. But what we can enable from that is actually with the Ctrla library, we can enable that device to be used by DAW software anyway, or plugins or whatever else. And that is kind of enabled by this abstraction of generic events. Other things that are very important to musicians and that were taken as requirements for the Ctrla library. We have, for example, Hotplug. If you're on stage and someone plugs out the lead of your controller, you want to plug it back in and it just work. It's kind of a requirement. You can't say, oh, sorry guys, I'm going to restart my DAW, restart Jack. I might have to reboot if it, So those are kind of things that are quite difficult to implement or to design in a way that is logical in your software, and even more consuming to test. So you'll notice that I talk about testing quite a lot, and that's from experience having developed these two particular devices under the Ctrla library. To make sure Hotplug works is an absolute head wreck. You plug that cable in like 1,000 times to check if it's actually stable, and then it crashes once. Well, next time, do you have to plug it in 2,000 times to make sure it's okay? So these are the kind of things that, just my own experience from having developed them, and I think hopefully, yeah, something that we can benefit from all as a community. So I showed you this image earlier of non-ideal, shall I say, mappings from hardware devices and various types of controllers to software in the Linux audio ecosystem. And this is hopefully, marketing slide, what we achieve from this. So what I'm hoping to achieve is that we can use MIDI devices, USB, HID devices, Bluetooth devices, OSC, and whatever else you can think of, Arduino serial based devices, have those all broadcast their events into the Ctrla library, and then have a DAW support the Ctrla library as an abstraction for events coming in and out. And in that way, we can actually support all of the devices, but we don't all each have to support this particular device. So as a DAW software developer, you support one library, and that library will provide you with access, or provide your users with access to their hardware, whatever that hardware may be. And as a developer, you don't have to worry about that. You ensure that the Ctrla library support from your software point of view is correct, and the user or the implementer of like the backend, shall I say, or like one particular device ensures that that maps correctly. And then we have a situation that all the way up the stack from the hardware to the DAW software should work. So that's the ultimate goal behind this. As an analogy, has anybody here used libsendfile or libsoundfile for writing WAV files and that kind of stuff? Right, I see a whole bunch of people's hands. Think about that. Why did you not write your own AIFF, WAV, import and export routines? Well, because there's a perfectly good library there, and you can save yourself a hell of a bunch of trouble. I see some shakes in the audience. Of course, some people like to do things their own way. I get that. And I'm not saying Ctrla has to be used by everybody. There will always be exceptions. But nevertheless, one of the first things I do when I start an audio project is #include sendh, because that just means you can import and export your audio and do tests and all that kind of stuff. So that's kind of hopefully what we'll work towards is this model of being able to support all of the devices. I'll jump right in and talk a little bit about users and mappings. I kind of see two types of users, or two types of workflows rather. As a novice user of any DAW software, you want things to just work. You're not particularly worried about having the most awesome show, live stage kind of performance. You're just trying to get your guitar recorded. And I'll call that the simple workflow. Right now, that's supported very well with relatively simple hardware MIDI controllers that provide MIDI mapping, or that the DAW provides a MIDI mapping for. or some way to do MIDI mapping as a user. You click a UI element, you move a slider, they're now bound, and that provides a workflow that actually works. So if we look at the simple workflow, what I'm hoping to achieve is that we can map these generic events from the controller library to a slider or a knob in the DAW software in that same way, that you move a UI slider, you move a hardware slider, the event that comes in will be triggered or will cause that link to be set up. And just like MIDI mapping, it just works. So for the simple workflow, nothing really changes. To the user, it's transparent that this controller library is in use, and it allows the user to achieve the functionality and the user experience that they desire. So it's not as powerful, but it achieves the goal, which is kind of the ultimate thing. The other use case that I see is a power user. So I know there's a whole bunch of people in the audience here who are happy to code stuff in C or assembly even, I don't know. There's also a bunch of power users. They're people who love to make music, who want to use this stuff on stage and have at least rudimentary programming or kind of concepts of programming and scripting. And they would like to be able to kind of script or kind of, you know, mush around some of these events and bind this particular controller not just to one event, but, you know, have more complex and more powerful ways of interacting with their hardware and their software. And that's the kind of the power user use case that I'm focusing on as well with the Ctrla library, that we need to provide a way to let these power users actually exploit their power user-ness, I'll call it, or rather their desire to provide really complex and powerful mappings for on-stage live usage. So the idea there is that the power user can script their controls, they have the flexibility and the power they require, and they create these awesome mappings for a specific device. So at this point, I'm no longer talking about generic events, but those generic events get mapped to a particular software by a power user, and then that turns into like a mapping script or whatever we want to call it. Once that's completed, if the user happens to have one of these same devices, they can use that script. So at this point, they just basically, I don't know, load the script, or somehow we tell the user, do you want to use this uber powerful script that somebody else made? And they say yes, and suddenly they have that same powerful interaction method, but they're not capable, or they didn't actually contribute to that mapping itself. So that kind of exists right now in various DAW softwares or plugins support specific devices. Like directly, shall I say. The downside that I see to that is that it doesn't enable that same device for the rest of the community. So it essentially causes, is duplication of efforts. If I want to support that same device in one of the OpenAV projects, I'd have to essentially recode the driver and retest it. That doesn't, to me, seem an ideal workflow as a community. So. As a final note about power users, there's a move in the recent five years or so with these types of USB HID modern controllers. Excuse me. There's a move to very tightly integrated hardware and software. And by that I mean there's guys, if you do a YouTube search for like live performance drum pad or something like that, you'll see these guys going crazy and hitting all these buttons, and there's like hugely multiplexed inputs. So if you press one button, all of the functionality of the device changes. Instead of playing a drum kit, you now have a synthesizer. And if you press another one, you have like a clip launcher style sequencer. So there's a huge amount of multiplexing or layers of functionality that you as a live performer, as a musician, can switch between. So that involves matching the software and the hardware to a degree that enables a really powerful workflow. And that's something that I kind of see this power user achieving. So the DAW software may already provide that, but not expose it in a way that is mappable to hardware or to the MIDI controller that a user has. And the idea here is to enable that by this scripting method I just talked about in the power user slide. So that depends very much on the hardware and the software in use. So if I have this device and let's say, I don't know, either as a DAW or Qtractor or whatever, the mapping that I want for this device to that software is probably not going to be the same mapping that any of you in the audience want. I have my own way of doing things, and I'm sure everyone else here does, that you want this button to do that. Why? I don't know, I just do. And that's kind of the workflow that this really tightly integrated software allows. And it depends absolutely on the musician's workflow. So I don't think there is a way for us to provide sane defaults that will work across the board. We can provide sane defaults, but we must allow some configurability, flexibility in how that multiplexing of all these controls works. So I'm gonna, well, will I? We're on 46. I have half an hour. Go on, we'll talk about a timeline, just for fun. So this isn't really about Ctrla itself, it's more about the development workflow of Ctrla. I won't talk through all the things, but suffice to say, I bought this device right here about a year and a few months ago, so January of 16. I have been toying around with trying to make it work with Linux audio. There's actually another project called machine.rs, which is a Rust implementation for that device. So I kind of took that apart a little bit, figured out what the author was doing. From that, kind of got inspired, wrote some C code that done approximately the same thing, integrated that with Fabla 2. I used that at the Mini-Lac in Berlin last year. So I had a little demonstration of Fabla 2, but also sneakily kind of worked with a little hardware controller. Found out that it's a nice workflow. I mapped a couple of buttons to have this kind of multi-layered complexity. It's really cool that you can do kind of powerful things with that. But I also realized as soon as I bought a different drum pad, that code was essentially irrelevant and I would have to re-implement all that. So at that point, I kind of came to the conclusion, look, we need to somehow abstract this so that not everyone ends up doing the same thing that I've done. I made the mistake of supporting one device directly. Not that that's a bad mistake to make, but that we need to consider, is it worth, like, can we justify the effort of supporting that one device in particular if there are so many devices out there? So I showed a few pictures there, but if you do a search on Thomann or Music Store or one of the big music companies, there are hundreds of these devices. And they all have their own unique properties and their own reasons. And I'm sure that like people in the Linux audio community have pretty much a range from 0 to infinity of these devices. So supporting a particular device, although useful for everyone who has that device, is not enabling the whole community as such. Moving on, summer 16, kind of worked on requirements, version 1 of the API last autumn, discussed it with some other people, designed version 2. December, so just December gone, let's say half a year ago-ish, really got down to developing version 2 of the API, implemented it. January, wrote some LAC paper stuff, that's also part of it, got ready for kind of what did I want to demo, started planning things. I integrated the Ctrla library with Mix. Mix is a large open source DJ software, really cool software, and essentially as a proof of concept of how is it to integrate the Ctrla library into Mix or into an existing large software that would benefit from this Ctrla support. Specifically Hotplug, so one of the items that the Mix guys have on the roadmap for their development roadmap is to support Hotplug of devices, so particularly if you're DJing and someone pulls out the plug, you want to plug it back in and have it work. So that's something that, as the Ctrla library, I've been really focused on to ensure that that gets enabled properly. And that's something that I tested while running the Mix code base and yeah, trying to figure out how can we make this all work together. So although it works, I don't have patches upstream just yet. I kind of hacked it because I wasn't aware of the Mix internals at all at the time. I am intending to open source, at least send those patches out, but also hopefully rework it a bit that it's not quite the hack it is right now. And I'm in touch with some of the Mix developers and we'll kind of communicate a bit and try and figure out what I'm doing and what I'm doing wrong mostly. So then between February and now, minor updates, building out some demo apps that I can show you guys what Ctrla is actually capable of. And yesterday evening, as I said, this code was all pushed up to GitHub, so it's currently available. And yeah, if you file issues, try and compile it, tell me it's broken and rubbish or something. Or fantastic, I don't mind either. Let's jump straight into demos. I have a couple of things that I'd like to show you. I'll list them out here. So first of all, let's talk about simple events. So if I press a button, we get an event in the application. There's a little sample application as part of the Ctrla library that will just print out what button was pressed and what the name of that button is. Really simple stuff, but essentially the basics of enabling an application with Ctrla library. Feedback, so how do we turn an LED on this device? Tight integration, so I'll kind of show with the machine here, I have a little demo app that's kind of a sequencer type use case. We'll talk about scripting and we'll talk about DJ Hotplug. So without any delay, I will jump straight into here. You guys can see that-ish, I think. Yeah, hopefully. It doesn't really matter too much, the exact code and things. I'd be happy to sit down with any of you after the presentation and talk through the details. For now, what I'll say is we've a couple of binaries here. I'm going to run them. I'll kind of talk you through what's actually going on. I don't think I'll show up any code because it'll get very deep divey. If there is questions at the end, like, okay, how specifically did you implement, I don't know, Hotplug or something, I'd be happy to drag up some code or the Doxygen and show you what the API looks like. We'll start with the simple application. So what simple does is essentially accesses all the devices that are available. So when we start an application, all of the devices that the controller library supports are probed. So it checks, is this device connected to the system? No, it's not. Okay, that's fine. If it is connected to the system, so that means like a USB device is plugged in, the application gets a callback that says, this device exists, would you like to handle it? So the application at this point can say, yes, I want to deal with this device, or it can say, no, don't want that device, I have no support for it, or don't wish to claim the device. So at that point, it'll be returned back to essentially not used state. What that means is if I run that application again, but this time I will plug out the USB leads of the controllers here, then what we'll see is rather than printing out a whole bunch of the state of the controller when we plug it in, there's nothing. Now, what I'll note is when I plug this back in, the application will automatically pick it up because it's a Hotplug. It's a callback that the application receives and can receive at any point. At any point, I mean when it gets pulled. I won't talk about threading models and things. If you're interested in that kind of stuff, come talk to me later. So the interesting thing there is if I run an application and I don't have my controllers plugged in yet, and I plug in all my controllers at a later date, that just works. There's no issue with that. Now, if I press buttons, we'll see that we start getting button press. It says the button, it says F1, so the label that's actually physically on this controller here is F1. If I press the scene button, then it should say scene. Fantastic. Live demo effect. Not yet, not yet. So we can see that various things work. If we twist the encoder, for example, we see encoder rotate messages coming by. If I press the grid, we see that whatever grid square is pressed is being pressed. If you press the encoder, there's actually a button under it, so that is essentially an ordinary button. It's just the fact that it's under an encoder doesn't make any real difference. So we can see that this device pretty much just gets supported. It gets these events, and the events are printed out. It's pretty simple, but as an application that just wants rudimentary support for the controller library, that's all it takes. I think the sample app is less than 200 lines of code. So it's a relatively easy, small amount of code to integrate. And let's see if we can figure out how to integrate these things with various other projects. For example, if I run with an argument, so I just ran it with 10 as well. I'll move out of the way here. So we're running the simple application, but we passed in an argument on the command line. And what that will do is light up a particular LED. So based on the number that we pass in there, if I pass in, let's say, I don't know, 16, then a different light will light up. So from the application point of view, LEDs are an integer ID, and you pass in a particular parameter, which tells it the brightness and the color to show the LED as. And depending on the capabilities of the hardware, it will utilize either the brightness if it's just if it's capable of brightness. If it's not capable of brightness, it'll turn it on or off based on a toggle. And if it is capable of color, it will interpret the color bits and display that our red, green, blue value instead. So with one API, we actually cover all the use cases of how can we turn on lights and turn off lights. That same goes for if I turn on 30, we can actually turn on the LEDs on the grid as well, and they're fully red, green, blue support. So if I updated the application a bit, we can get colors showing on this device. Now, instead of showing all of essentially that's the simple events and simple feedback, what I'll do is I'll jump into the tight integration demo, which is this sequencer binary here. And I'll hold this up for the audience. Hopefully you can kind of see a little what's going on. What we have is, it's a step sequencer, so hopefully you can see the white little light floating by. That's the steps that are going to be played, and this outputs to ALSA MIDI. So what we have is a device that was never supported on Linux is now using the controller library. We have an application built on that interprets these generic events, and from these generic events and some sequencer code, can output ALSA MIDI events and actually enable a musician to perform something with this. If we do some fancy things, we can press the shift button, and we can select different pads. So if we select the kick drum, then there are 4 kick drums. If we select a snare, then we have some snares here. Similarly, we can select any number of these and work out, okay, what's actually going to be played. Now I'll tap in some random little pattern. If we switch, we have two buttons here. This is pattern mode, which shows us the pattern per particular device. If we switch to pad mode, we can see that the lights that you would actually play in pad mode to light or to play that rhythm are actually lighting up. So this is where user experience kind of combines itself with the power, or rather with the tight integration part, that if you press one button here, it determines what this grid does. So the actions and the feedback on the grid changes its behavior based on the buttons being pressed. That's something that's really hard to achieve doing MIDI mappings. So it's kind of the core demo of what I'm trying to showcase here. If we press this group button, we can select various different modes or kind of colors or whatever we want to call it. And that same, so the device reacts differently based on a different kind of mode. Again, what I'm trying to demonstrate here is layers of complexity in a single device that a musician can use on stage. So instead of having 3 of these devices and having to like manually use different ones, we can multiplex that same functionality into the device and provide a live performance workflow that is actually much better and much more capable for the Linux audio users. So that's the kind of the tight integration element that I'm trying to promote, particularly with the Ctrla library. Now, I think there was a question at the back. Is that for now? Go on.
Yeah. Really to what you're saying right now. This functionality you're showing here, is that the controller working, or is that your algorithm instructing it how to act when you click the buttons?
So I'll just repeat the question for everyone on the live stream. The question is, the thing that's running here on the controller, is this actually in the controller, or is it my algorithm in the application that is doing the actual logic? So it is the application. Every LED that's being turned on or off, right, on this, anytime I press a button, it is a generic event being sent to this application. The application understands the event, does a specific action, and based on that is going to update the state of the controller. So all of these LEDs are being refreshed every single frame. So when anything changes, all of the lights are actually updated. That's the way these USB HID devices work. So that's not fundamentally a part of controller, but from understanding how this device works, it's quite interesting that when we press this one button, it's one USB message gets sent to the cable, and suddenly we have all of this lights in those colors. So they're well designed for this type of use case, but essentially it is application logic that is performing this sequencing and light changing on the device. So it's not that the device is smart. Actually, I'd argue that these devices are almost simpler than USB MIDI devices, because often the MIDI devices, when you press them, they'll light up the LED behind the button themselves in the hardware and send a MIDI message over the cable. Whereas with this device, when I press this button, nothing happens. The light doesn't turn on. So the light will only turn on if the driver or the application code on the other side pings back a message and says, oh, turn that light on. So they're very, you have input and output, and they're very separate unless your application glues those things together. So this kind of comes back to, we need to think about user experience, and we need to think about workflow for both the novice or the simple workflow, where we need to provide this. There's no way we can require a musician or a user to do this themselves. But we should also focus on the power user who may want to, rather than have this button light up when we press it, have those 4 buttons light up 1, 2, 3, 4 of their house tune, so that they always have a visual metronome. So those are the kind of use cases that that I think we should be looking to enable, and that essentially the Ctrla library with this software does enable. So that's kind of a long-winded rant about your question, but thanks, good question. So that's the tight integration. Now for the probably most dodgy part of this whole demo. What I'll show you is there's yes, absolutely most dodgy part of this presentation, because I need to go build it. So you can all watch me live code for a second. Free live coding performance, by the way. Ctrl, let's see, make lists. And bear with me, please. No, I was right the first time. I have this TCC scripting was off, and now I'm turning it on. cd build, cmake cache.txt, cmake ... There we go, and let's build that up. And now, hopefully, woohoo! It worked. So I should probably talk a little bit about what I'm going to show before I show you it. TCC is the tiny C compiler. It is a small library that is available as a standalone C compiler that's really, really fast and lightweight, but it's also available as a library. And by a library, I mean just like lib sound file or something like that. You link against this library, only what you're linking against is a compiler for C code. So what you can do is at runtime of your application, you can recompile C code, pull out function pointers to that C code, so the functions that you've just compiled, and execute them. What that means is that we can provide a workflow for a power user or somebody who's comfortable enough writing some C code to, instead of have to recompile the entire application every time that they want to make a change to their controller script, instead they can write this controller script using an API that the application provides, and these generic events can be thrown across into the script, and the feedback can be pulled back out from it. So with TCC, what we enable, without talking about the techie details anymore, the workflow and the use case that is enabled is a power user who has a big DAW software that they know how to compile, but they're not comfortable enough literally hacking the C code, recompiling the entire application, waiting for those couple of minutes while that happens, then testing if this button actually works, no, it's still not right, and having to recompile the entire application again to update their script. What this TCC kind of concept allows is that controller handling, or the handling of the particular generic events, to be outsourced to this C script instead of C compiled in source into the application. And as a result, we can actually live code C and have that update the controller. So, okay, talking is over for now. What I will do is try to grab myself another terminal window. So I'm going to need two terminal windows for this because one is going to run the TCC script. Build examples. So I'll run that in this little, right, nice. CD Ctrla scripts. Bear with me, one moment. NID2, --build examples. So this is still relatively, it's kind of a new concept. I'm still dabbling with the exact details of how does this API between the application and the controller work. But what should work now is that we see, one moment, cp Ctrla / into build examples and cd build examples. Yes. So what we just done is we ran this TCC script binary, and anything that says TCC script example will basically be from the application itself. It says compiling NID2 script.c, so that's this particular controller here. And if I move this device, then it doesn't work because it's not plugged in. So I get to demonstrate Hotplug again. There we go. Pops up. It says accepting native instruments control D2 script blah blah blah. Perfect. And if I now move this, we see that it says slider 0. It also says button. The reason for that is these are touch-sensitive faders. So if I touch it, it sends a button event for you are now touching the fader. Then it'll send some slider events, and when I release it, it'll send the note off equivalent or generic event button not pressed. That works for all of these. So I have various pads, I have encoders, I have filters, I have a whole bunch of stuff here. And what you see is a generic representation of a slider event arrived, and that slider event ID had number 4. Now, what I'd like to show you is if I open that script that I just copied into that directory and blah, 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 this is what it looks like. The top bit is a little bit nasty. I'm still working on the exact implementation details. But the interesting part is essentially this, which I think most C coders here will be quite familiar with. I'll get out of the way. Yes, we can just about see it. I'll move that single break statement, and then we're good. There we go. OK, so most of you are probably familiar with a callback function. Every event that occurs, this callback function will be called. It can be called with a number of events for performance reasons. We can batch 20 events into one function call. We loop through the events and basically switch based on the actual type of the event. Controller event button, well, that's a button event. Then we can check the event, dereference the button from it, and pull out the ID. So the ID is which of these buttons is it. And then based on whatever case we have, we can print out, OK, this is the button called Flux or Remix. So I'm going to press a button, this one. It says capture. Now, if I switch back to the terminal that's actually running this, it's saying button 28. Because the script right now, if we check the code, is not aware of anything here of number 28, and it doesn't have anything to print. So the nice thing here is if I jump up here, I'm going to copy this line. I'm going to change this to 28. And I'm going to change this to say capture. Yep. for those not familiar with Vim, I just wrote the file, so the little W thing there, script written. So we've essentially updated this script file. The binary that I was previously running is still running. I didn't close it, I'm not changing it. We update the script file. This application pulls that file periodically, and if I now press something, it'll say, boom, recompiling script nid2.c, TCC script example, blah, 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 button, whatever. And now if I press the capture button, it prints capture instead of 28. Thank you. So from a scripting point of view, we've just saved ourselves hours and hours of mundane recompiles to check if a button does what it does, change some code, oh, that should be a little brighter yellow if I want that to be seen in a daylight situation, rechange your constants, this kind of stuff, recompile, test it. So instead we've changed that workflow to being, I'll just go over here, we'll change this case to, let's say, the remix button, see if that one's working yet. Okay, that's 51, you change this number to 51. You change this to say whatever you want. And then you press the button, and it works. So the development workflow has been hugely improved. And the turnaround time to develop these scripts is insane. It's fast. Now, there are downsides to this. This used to be stable. I think if I put syntax errors into the code now, it crashes. I was investigating this yesterday evening. I don't think I got the bottom of it yet. Having said that, that's a temporary thing. I tested this live scripting component with the Mix code base. So that was a previous version of the same API of the Ctrla library. What it really allows is us to pull numbers out of the Mix engine. So the Mix engine is kind of built for that. They're really designed for controller support. You can pull values like where's the crossfader position or what is the volume of a thing of a particular track playing. You can pull them all out as floating point numbers. And you can display them on your device really, really easily. And for input, you get this generic event, and you can say, I want that play button to cause to set this particular component in the Mix engine track or channel 1 play to on. And that will essentially cause that track to start playing. So the interface between Mix and the controller library is really nice. And for developing things, because we use this TCC, we have a situation that those scripts can just be reloaded, recompiled on the fly, and developing a mapping for a really complex device like this D2 took about a day. And by really complex, I mean like we've multiplexed all of these buttons so that we have hotkeys, loops, you have various controls, filters, everything is mapped. And if you press certain buttons, you can switch deck, and the whole device now mirrors to 4 decks or various other features. So the power that we gain from this TCC scripting to actually write our scripts, particularly for power users who are familiar with some kind of scripting or compiling, is really cool. And when I realized that, I kind of came to the conclusion, what if we don't try and enable a scripting language? What if we don't use, so the Mix engine uses JavaScript, various other software in the Linux audio community uses Lua or Python bindings, or I don't know, there's another few, they're not coming to mind now. So those scripting languages all allow interacting in some form with real-time threads or with real-time info and non-real-time info, and it takes the developer some time to develop that actual scripting API. What I'm intending on doing, at least in the OpenAV software, is using TCC to provide a C-style scripting interface, because what it allows us to do is once we have a script that we're very happy with that supports the device in a particular way that you're calling official, we can compile it into the application. And it's suddenly no longer unoptimized scripted C code with function pointers, but we can literally code it into our application. And as a result, we get very performant code. And for things like the screen on this device, I think that's probably a benefit. Now, that's not to say that you can't script the screen from TCC. You can, I've done it. And I just see that as a longer term solution of if you really want to go on stage with something, there's no reason you can't use TCC, but I do like the idea of having a binary that doesn't require libTCC for a few reasons. One, you can deploy on very minimal systems, Raspberry Pis, that kind of thing come to mind. TCC does support the ARM target, so it is possible to also compile using TCC on various platforms. But I don't know, is that something you really want to do on your production machine? Maybe you just want to ship a binary over there and you know exactly what version is compiled into your application, and that's what you call your golden copy and actually perform with. So there's a bunch of kind of details there. if anyone's interested in chatting more about how to enable this TCC stuff, it's kind of detailed in the paper about Ctrla a little bit, but I'm happy to talk. There's the TCC example code as well in the Ctrla repository. So again, open source, have a look. Questions, of course, do let me know. So that's a lovely little bug. Let's not talk about that. So that's scripting in C, item 4 from our list. The last one is DJ Hotplug. It's a bit of a marketing term, but hey, we'll run with it. So, sorry, I turned off my own. Okay, as the next demo, I'd like to demonstrate what both of these devices can actually do in a real context. So, cue audio on the sound system. And here we go. All right. Loud enough? Louder? Louder? All right. So what I'm going to demonstrate is a tune that I created using LMMS, fantastic piece of software. Bash some tunes into there, create some housey, dubsteppy music, whatever you're into. What I'm going to show you is a demo application, probably the most fully fledged Ctrla demo application that I built. So what it enables is a DJ interface like this to actually perform like a DJ interface would in real life, shall I say. So with that, I'm going to demonstrate playing a track. We're going to talk about hot cue points and things like that. For those familiar with stems mixing, these 4 faders all control individual tracks, and you can actually take individual items in and out of your mix. So there's a whole bunch of cool stuff going on here. For example, hi-hats. Some filters. And that functionality is also controllable from the other device. So what we'll see is, I can't really hold both of these up, but let's try anyway. If I press the play button here, we'll see the state is updated on both controllers, providing the user experience that you'd actually expect. If I turn the filter LED on over here, we'll see it's shown on the screen and on the other device. If I turn it off, it gets toggled off on the other side. It's basic UX stuff, but it's very important to actually provide good user experience. So I'll take the volume down just a touch. So right now what we're at is a point where we're playing something, and we'll set a hot cue point so we can skip back to there. Next step, toy around with some filters. But hey, wait, somebody comes along and pulls the plug out of our controller. So this device is no longer quite working, right? But if we plug it back in, we're right back running. That's the hot plug that you require as a musician when you're on stage. You plug back in, you're going again. Your show hasn't stopped because Ctrla actually dealt with the hot plug of the controller. That's the Ctrla demo. I realize I'm pretty much 30 seconds from time, so I'm going to run through this. Next things are discussing event loops, so that's been raised by some people. Absolutely very important discussion. How do we integrate this from an application point of view, threading event loops? How do we, or do we integrate with LV2 atoms? How do we get applications enabled using this? How can we discuss the sharing of devices? So right now, each application has exclusive access to a device. Is it possible to have 2 applications share a device? Of course it is. Is it worth the effort? How does that work? All things open for discussion. Backend support for things like Bluetooth, for a Wiimote, for MIDI, like generic MIDI devices, for OSC, Arduino, Serial, keep going. So I think to see where I'm trying to go with this, I hope that the demos actually make you want to kind of code a bit and toy with these hardware things. If you want to take the loan of one of these devices for half an hour later and sit down somewhere and code with it, please do come talk to me and I'd be happy. At this point, I'll open the floor to questions because I think I'm pretty much out of time. But thank you very much for listening. It's been a pleasure talking to you. Yes, we have questions.
Do we have a microphone?
I can repeat them otherwise.
I actually have 2 questions.
All right.
First is about notes.
I'll repeat the question. Yeah, my bad. Yeah, Philip.
Okay. So first question is about notes, because if you're handling MIDI devices, because some of those devices are still MIDI, you want to handle notes as well, because otherwise you have to handle the MIDI messages as by yourself and also have the controller. So you have to support two APIs, kind of.
Agreed. So you're saying integrate note on and off messages into the controller API, essentially.
Yeah, notes and pitch bends, I guess, and then...
Okay, make it MIDI backwards compatible, you're saying, as in have those same events reflected in controller. I hadn't considered it. I will consider it. I won't give you an answer to that right now. I don't know yet.
Yeah, the idea is just they don't have to support two different APIs.
I understand your motivation. You had another question?
The second question is about the name. You keep mentioning that it's Ctrla, but you actually wrote Ctrla?
Controller, yeah. So this comes back to the OpenAV naming scheme, which is 5 letters and an A at the end.
Yes, but you changed...
Yeah, it looks nicer, it types nicer, you know, there's various reasons. I mean, if you type an entire API, you're going to be picky, right? The order of the letters has to be correct. No, it is what it is.
Usually the short name for control is CTRL?
Yes, and the first version of my API was called that, but I realized it didn't adhere to the naming scheme. And if you're updating between two APIs, it's really useful to rename it so everything compile fails. And then when you update, you can actually catch all of the function calls. So 2 reasons, one technical, one purely for enjoyment. Thanks, Phil, good questions. There's a question, both sides.
That looks really interesting. I have also 2 questions. One would be about discoverability. You have these kinds of events. Are they just, which are coming from the devices? Do they have some kind of textual representation somewhere, or is that entirely optional and up to the application?
A textual representation of the event. So the events are generic events. They're very small C structs. So it has an ID or a type, which is it a button, is it a slider, is it a something?
Right.
It has an ID, which is which button, which slider, or which. And then there's a union based on the type of, is it a slider or a grid, is it a float or uint32 or an int32 as to what it actually does. Right. So there's no textual representation, but it's really, really easy to print out or to serialize.
So that's in the driver somewhere, or in the interface to the device, it defines these things?
Yes, so the entire interface to the controller library is defined in controller.h and event.h. Controller.h is like your poll devices, accept functions, those kind of things. The event.h is the events that you will be receiving and transmitting from, and they're very, very simple C structs. So I think, like on purpose, I kept them as simple as we possibly can for reasons like creating bindings to other languages, if people feel that's something that they desire, mapping to LV2 atoms. So there's quite a nice match between that struct, because it's a static struct, that, like, you know, it doesn't change. It's
mapping to OSC,
for example,
some kind of textual representation there. So
absolutely possible, yes.
So that one thing that I'm thinking about is really having something like osculator, but based on this library, completely generic, whatever device it supports, but then you have a dynamic aspect, so you have to find out about the kinds of events that you're going to get.
Yes, so as part of the descriptor for each device, you get a list of, okay, the device name, the vendor, the blah, 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 but also the number of each type of control. So if you have 20 sliders, then it gives you the number, there are 20 sliders, and you can query the name of each slider. So it gives you a string representation of that particular control back. So there are ways to communicate that metadata with the device through the API, absolutely, yes.
And a short second question, how much code do you need for implementing a typical controller like the machine control
the back-end implementation, you mean?
Right.
It's relatively simple. It depends, of course, on the device. So there's abstractions for things like UI or USB input-output. So you register a callback saying, I want this function to be called whenever there's USB bytes available. With these devices, you write a big switch based on the size that comes back. It's either buttons or sliders or whatever. And then you need to decode that and ping the events away. So it's not particularly terse, but the larger and the more complex the controller, the more code there will be.
Right. So how many lines?
I don't know offhand, but I can check very quickly for you. So CD OpenAV. Maybe hand the mic to one of the other, or if you don't have more questions.
Do you have timing information on the events?
Do I have timing information on the events? That's a very tricky question. It's actually in my bonus slides right at the end, I think. I will skip all the way down and say timestamps. Woohoo! It is a, yes, it's something that I've thought about. I don't have a good answer to your question. I would like to discuss it with some of the time developers of the community here. Based on threading models and how libUSB and other implementations work, it's not always easy to get a timestamp that really gives you what you want, because you end up blocking some threads sometimes, or not blocking threads, or using asynchronous I/O methods. Where do you sample time is a bit of a tough question. That said, I don't see any reason why it could not be achieved. I haven't looked into it much. Right now, from a live performance point of view, I don't see a huge amount of requirement for it because we're not recording them. If the application wants to record them, it can. So what you end up doing from the end of this switch where you handle the incoming USB messages, you call the callback into the application to handle the events. So the application can timestamp the events almost as good as the library can. So there's kind of pros and cons to both. I do agree with adding a timestamp value into the event so that the application could even repurpose it and just do a mem copy of the event and add a timestamp at once and use that as a sequencer so that it could actually become a sequencer event. Again, this is all kind of open to discussion. If you have input, absolutely get in touch.
Is there semantic mapping as part of the controller? Like at one point you showed like pressing the play button on one device and it also showed the play button on the other one.
Yes.
But they have different button IDs, I guess.
They do.
Buttons. So there's...
Is there a semantic mapping? Currently, no. That was in the application. I pretty much played a prank on all you guys and happened to have coded that button to that. Now, there's two answers to your question. I think one, adding that complexity to the controller library might not be the correct place for it. I did in the version 1 of the API have a concept of that where everything would have a string mapping and we could click these together. Right now it doesn't work that way. Based on the power user scripting mode, I'm kind of hoping that if that's what a user wants, they'll be able to script that themselves, assuming they're technically proficient to some degree. If it's something that's particularly of interest to people in the community, let's discuss and see if we can.
Without semantic mapping
right.
On the controller level.
Yeah. All right. There's one more question there, and yeah, I can.
I can do without a big.
Yeah.
Noticed you were loading all the demos as root.
Yes.
Does it mean there's still problems with permissions?
Quite honestly, there's two answers to this question too. Yes, I've heard, the question is that I was running as root and if there's issues with running as a normal user. I get shouted at a lot because I always run as root. So quite honestly, answer A to that question is I don't know if there's user permissions because I always run as root. Answer B is yes, I've heard some feedback from others in the community saying that you have to do some UDEV rules to actually enable user access to these devices because it's not automatically granted by the kernel. And that either requires admin rights or to copy some of these UDEV rules into a specific location. So perhaps this could be something that's done at boot up time or when apt-get installed this package. It also installs those UDEV scripts. I'm not quite familiar with UDEV and things like that. If we really roll this out to users in the community, let's discuss this and let's figure out the best solution. So very good question.
Then one more. If that's okay.
Until I get kicked off, I'll be here.
How's the situation with latency? I can imagine if you have a big screen that you need to update or lots of pixels, then you might want to prioritize other buttons or...
Yes, very good question. So this USB device, I'll speak with my experience. I don't have a lot of experience with lots of USB devices. This one implements two USB interfaces actually. So it has an interrupt endpoint and a bulk endpoint. The difference there being that the interrupt will cause basically the CPU to actually send that message immediately. That's used for the lights and for the feedback from if I move a slider, that sends an interrupt back up. So those are low latency and high priority events. On the other hand, the screen is a bulk endpoint. That means that it's essentially the same as a USB key or USB hard drive uses. It's optimized for size and gets deprioritized when one of the interrupts comes along. So yes, very good question. How about latency for the screen? If you just pull a thread on pushing updates to the screen, you get above 30 frames a second. I think 40 something frames a second. That said, that's full PixMap updates to the screen. They get deprioritized based on other things. So it essentially, I'm saying it gets handled by the hardware. The prioritization of the lights and the faders over the USB bandwidth for the screen is automatically handled by the USB protocol.
But just in this particular case, if you
Yes.
have another thing, it might not. If another,
So again, I'll talk from experience. If a device is designed that doesn't automatically happen, then yes, that is the case. I don't know what to do. It'll be up to the implementation for that specific device. If they have two USB bulk endpoints, maybe you can prioritize one over the other. If I don't know. I think most people designing these type of devices will probably do it this way. It makes a lot of sense. So, yeah.
So I think we have to stop now. Since